Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Don't have a lot to say in my introduction like usual, so we'll just dive in. So Misha Belenko from University of Texas Austin, who won Best Paper at KDD, and will, I guess, tell us about that a bit. And he may have one opening, he's here today and tomorrow, may have one opening tomorrow, so if anybody wants to meet with him and isn't currently meeting with him, send me a mail and maybe we can swing it.
Yeah. Actually, if more people want to meet, I'm leaving pretty late tomorrow evening, so people can pad the schedule on the above site too.
Yeah, so send me a mail.
Okay, thank you for having me. So I will talk today about learnable similarity functions and the applications that they have in information integration and clustering. So one thing that hopefully you should have seen before in many problems you work on is that similarity functions are quite useful in many problems in data mining and AI. A few examples, a couple of which I will cover quite a bit today. One is record linkage, where the very problem is defined as finding those records in the database that are highly similar to the point where they refer to the same thing. Another example is clustering, where the task is to split a data set into groups of objects that are very similar. Nearest neighbor search, or approximate duplicate search, or there's other names for it, is the problem of finding objects in a data set which are most similar to a query object. And again, related to it as information retrieval or just web search, is not necessarily web, but search is where the task is to find documents that are similar to a query. And the common thing here is that all of these tasks, they rely on some functions, some similarity function, which needs to be computed for the task to succeed. So a couple of examples of very commonly used similarity functions. Two large groups here. One is that we call off-the-shelf similarity functions. That is, they're just taken from a textbook or from a code base and plugged in. Examples are such as Euclidean distance for numerical data, Hamming distance. For text, you can use string added distance or cosine similarity. And the problem with them, of course, is that they're off the shelf. So if we want to adjust to the data set at hand, we can use functions that are very sensitive or data driven. That is, they adjust the computation of similarity to a given data set. Mahalanobis distance is the variant of Euclidean distance where you take covariance into account. Cosine similarity with TF-IDF weighting can be used as a very sensitive variant of just normal cosine, since you're taking the frequency of various terms into account. And finally, there is a large group of methods which explicitly take the space in which the data lies, and they somehow try to modify it, transforming it according to some objective function different for each one of these to hopefully make the data space more appropriate for some task.
Is it crucial for the second step that the information that you're using to derive a variant has to be from the same data set, or can it be done from a different data set? In that sense, is it really data-driven, or is it just some other statistics?
Well, I mean, we can play with the definitions here. I think the key thing is that it does not necessarily, it can come either from the data set itself, or you can have external supervision. So actually, what the talk will be on mainly is using external supervision, that is not just the data itself, but also some sort of human labeling in one form or the other to do this. But I sort of view these as, I view this, the pure data-driven, as a first step towards more learnable similarity functions. So let's look at one example where similarity functions are used. This is record linkage, and the task is, as I mentioned before, defined as finding objects that are referred to the same entity. And here we have a sample of a database that describes restaurants. And here the problem is that we have multiple records that refer to the same object. And here we have two example pairs. And what this here shows is that really there's two kinds of similarities that are necessary to perform this task. First of all, we need to take individual fields, name, address, and so on. And then for each field, we need to compute similarity between the values in that field. And then to combine these, we also need to look at the similarity across the fields and then put them together in some record similarity function. And what we can see here is that the notion of similarity for every field is different. So here we have some character edits. Here we may have some small character edits. Here we can have whole strings that are synonymous yet different. Here there is very vague notion of similarity, which is really not very meaningful in a lot of cases. And at the same time, different attributes have different influence on the overall similarity of records. So ideally, what we want to do is we want to learn similarity functions from data. That is, we want to figure out what is important, what is not important using the data we have. And in the talk, we particularly focus on labeled data, not just the data that is provided, but also some sort of supervision. Because it really provides us the appropriate notion of similarity for a given task and for the given data set. So for example, for record linkage, if we have examples of strings that are coreferent, that are duplicate, and records that are duplicate, that tells us what similarity should be. Again, for clustering, if we have clusters and examples of points that lie in the same cluster, they tell us what similarity function should compute as similar. In nearest neighbor search, if we have examples of instances and the objects that are their true neighbors, that tells us what similarity function should compute. Just like in retrieval, again, if we have examples of correct results for a query, this is supervision for training a function. And the bottom line is that similarity functions, they will do the best for any given task if they are learned from data, hopefully supervision data like that, and then utilized in a task such that they can also learn from the labeled data within the task. And in the rest of the talk, I'll talk about a couple of tasks where this is the case and show a couple of domains and methods for doing this. So first, record linkage, where the problem is defined as finding records that are syntactically different, but they refer to the same entity. And in information integration from multiple sources, which is sort of a large research area that can include anything from combining information on the web to merging multiple databases, it's really an important problem because if it's not solved, basically data is dirty, and a number of things go wrong. And there can be a number of reasons for why the problem occurs in the first place. Data have different format in different data sets, in different sources. There may be abbreviations, errors, and so on. And all of these lead to this fact that the same thing is referred to by multiple records. So here's another example of this problem in a different domain. Suppose you have a system which performs product normalization. That is, it takes offers from multiple merchants and it combines them into a single database where hopefully the offers for the same product are linked. So here, if we look closely, we'll actually notice that there are two coreferent records here are extremely similar to the one in the middle in between them. But they're actually different because this one comes with a lens, these ones don't. But at the same time, the textual descriptions are extremely similar. The brand is the same. The price is actually less similar between the duplicates than for the non-duplicate, and so on. So this illustrates that the problem is actually extremely hard, and solving it requires really figuring out what are these features that make certain things duplicate and others not duplicate. So this problem has been looked at for a very long time. Statisticians have been first to consider it in the context of matching census data and medical record data. And then in the last decade or so, computer scientists have started looking at it. And one thing that you notice from the references is that every person who's been working on it has been coming up with a non-unique name for it. So by now, we have this very nice list of different names, so which is a rather hard record linkage data set on its own. And none of my work can still figure out how to do linkage on this. So that's one future work aspect. So how do people generally solve record leakage problems? Typically, systems proceed in stages where, first of all, given a data set, it doesn't quite make sense to compare all pairs of records for similarity. So what we need to do is do blocking, which is this trying to identify candidate record pairs by dividing the data set into overlapping sets of records that are roughly similar. And as a result, we get these blocks where records are compared within each block. In the next step, we take the similarities between all record pairs that are within the same block and compute similarities, forming effectively this graph where the edges have the weights corresponding to the computed similarity. And finally, given this graph, there is this problem of somehow partitioning it or clustering the data, if you will, to identify the pairs or triplets and so on, or cliques of records that are actually duplicates.
Are you assuming that this blocking is essential because you don't have a primitive operation which gives you all pairs of records which are whose similarity is above a certain threshold? Is there any assumption when you say this is a general record linkage framework or?
Doing this would be a form of blocking. So having a primitive operation would be a form of blocking.
Not necessarily. Yeah, but we can take it off.
Okay. I mean, I think the having the overlapping sets may not be necessarily the way that the given blocking function performs, but the general problem of taking the entire pairwise space and trimming it, that's what I view as blocking. So we can talk.
So actually, I had a question too. Is the blocking just for efficiency, or do you also get better results by having this pre-cutting stage?
So typically, if your similarity function is, you assume that your similarity function is better than whatever the rough similarity measure you're using for blocking. So really, it's mainly for efficiency. I mean, if you're also losing accuracy by blocking, it's a problem, really. So, yeah. But actually, there'll be a part of the talk on blocking at the very end. So if you have, I'll cover more about it later. So one thing that's you notice that in all these stages, similarity functions play quite an important role. That is, they're used for blocking where we need some rough notion of similarity to trim the pairwise space. We also then need some notion of similarity to compare the individual fields within the records. And then we also need to combine the similarity between the fields into the overall record similarity. Therefore, it's important to have good similarity functions here. And what we'll argue is that it's actually good to learn the similarity functions from examples. So first, let's talk about how we can learn better similarity functions for comparing individual record fields. So string data is extremely common in most interesting realistic data sets where the record linkage problem occurs. And the couple of large groups of string similarity functions are vector-spaced methods, which are more appropriate for longer strings and text documents, where we take strings and lose the order between the tokens after splitting into tokens, and then map the data into some high-dimensional space, and then compute the similarity between the vector representations in that space. However, the problem is that by losing the order, we're losing a lot of information. And if the strings are short, it's really more useful to use sequence-based measures where we're taking the order into account. So there, we take the strings and split them into characters, words, tokens, n-grams, and so on, and then view them as sequences where similarity is computed as edit distance between these sequences, where edit distance is the minimum number of basic edit operations, such as deletions, insertions, of substitutions of elements, that is required to make the strings equivalent. So the basic example is Levenstein to Levenstein. It requires one deletion of h in the first string, and the 12/8 str to 12/8 street is distance 5 because it requires 2 deletions here, 1 substitution of dot for e, and then 2 deletions in the second string. So Levenstein was the first person to propose the formulation like that. And one thing that's important for the rest of the talk is that the computation of distance corresponds to some minimum cost string alignment, where we're taking the 2 strings, and then we're trying to find this alignment where the 2 strings effectively are side by side, and there's the bipartite graph matching them. And the cost is associated with every edge in this bipartite graph. So every operation here has some cost that's associated with it. And this can be computed effectively using dynamic programming for any given pair of strings. So improving string edit distance, that is adapting it to a given domain, requires learning the costs of these different operations that are needed for matching the strings. So 2 hopefully convincing examples are, for phone numbers, it's clearly insignificant to have a substitution of a slash for a dash or any punctuation for that matter. Well, for names, for example, rarer letters like Q tend to be more significant than less rare letters, and so on. So Risted and Yanulis in '97 have proposed an algorithm for learning operation costs for basic string edit distance, and they've modeled it as a one-state hidden Markov model, or an HMM, where the individual operations correspond to emissions from the one state. And the distance between the 2 strings can be modeled as the probability of generating a sequence of such edit operations that aligns any given 2 strings. So one issue with the basic Levenstein distance is that in natural text, a lot of variation occurs to consecutive changes. So in other words, you have multiple either letters or you have multiple words that are inserted or deleted at the same time, sequentially. And really, the basic model of Levenstein does not capture this because they're counted as individual operations. So to solve this problem, what helps is if we have this notion of affine gaps, which have been first introduced by informatics researchers. And what this does is that it assigns an affine penalty for consecutive insertions or deletions. So basically, for any gap like this, we will have some high start cost for opening the gap. And then for every subsequent character inserted or deleted, we just have a smaller extension cost, which is being added. And the computation is done similarly as basic edit distance with dynamic programming algorithm. So therefore, it would be quite nice to extend the Ristad-Yanilos algorithm to do this, since for natural text, this tends to be a much better similarity function. And here's the model that does this. So this is a pair HMM, which computes learnable edit distance with gaps. So instead of a single state, you have 3 states. You have one state here, which performs the matching and the substitutions. That is, it generates pairs of characters or tokens, if we work with token edit distance, that are either substitutions or matches. And then we have these 2 states, I1 and I2, that are responsible for generating gaps. So I1 will generate gaps in the second string, just generating characters from the first string. And I2 produces gaps in the first string by only generating characters in the second string. And in this model, if you're not familiar with HMMs, you can think of it as a finite state machine with probabilistic transitions going between the states. And then there's a distribution of the emissions coming out from every state. So this model will generate all possible alignments for any given pair of strings. And we'll show this with an example. Suppose we have the same 2 strings, 12 8th Street and 12 8th Street, and we would like to find the similarity between them. And for this, we'd like to see what are the possible alignments. So this model can generate any alignment. So let's look at one possible alignment that can be generated from the model. So the model will start in state M, and here it will generate the pair of characters 1 1. And then it will transition to itself and continue generating these matches of characters until we get to this point where there is the TH in the first string, when the model can transition to the gap state here, and then generate the gap, returning to the matching state, and then continuing to generate the pairs of matching characters until this point here, where there's a substitution, which can again be generated in the same state. And finally go into the insertion for the second string, where the gap is generated here, and then finally the alignment completes like this. And so the costs in the original model here, will correspond to the probabilities of omitting this individual pairs of characters in this model, while the gap costs will correspond to the probabilities of transitioning to the insertion states, and then the probabilities of self loops or self transitions in the insertion states. I'm sorry? The taus, so these are the probabilities of ending the alignment at any point. So here we have really 2 parameters. There's the probability of ending the alignment with a gap or ending alignment with a substitution. So they're not extremely useful, but in some cases where the alignments tend to end more with gaps or more the substitutions, they may come handy. So given such a model, a similarity between strings can be viewed as the likelihood of all possible alignments between the 2 strings. So given 2 strings, there's basically multiple sequences of these transitions and emissions that can generate the 2 at the same time. And here what we'd like to do is basically sum the probabilities of all these alignments and then normalize by the probability of just observing the 2 strings, which can be viewed as the normalization by length in the original edit distance model. And the nice thing is that this computation here can be done efficiently using effectively the same dynamic programming algorithm, which in this case is the forward-backward algorithm in the HMM. It's also possible to use Viterbi, but we have found that Viterbi does worse simply because in some cases you have multiple alignments which have high probability, and if you're just choosing one, you're effectively ignoring the others. So as I said before, the operation cost corresponds to, in the original model, corresponds to the negative log of probability in the pair HMM, which makes the algorithms effectively equivalent to the original model. And actually, in bioinformatics, people have been looking at algorithms like this for aligning DNA and protein sequences for quite some time. Durbin's book is a really good reference for probabilistic models in bioinformatics. So what we'd like to do is use this model in record linkage for computing similarity between individual fields of records. And there, what's nice is that we can have training data. We can have examples of strings that are aligned, that are known to be coreferent. And in many domains, this can be achieved by some data having unique identifiers. So if we have these records for offers, they have a UPC or the barcodes. If we have people records in censuses, for example, we can have social security numbers If we have books, we have ISBNs. So if we have some data where the records are different, yet they have this unique identifier, this is effectively training data for this model, telling it that the probability of these things being aligned should be very high. If we don't have such data, we can always hand label and then just get training pairs of examples that are co-referent, that are duplicate. So then given such training data, we can use an algorithm such as expectation maximization, EM, to learn the probabilities of transitions and emissions in the HMM model. It's actually possible to use other variants of training other than EM. For example, if we want to also incorporate negative training data, that is, we have some pairs that are not co-referent, and we also want to explicitly make the model give low probability to such pairs. And as a result, after we do the learning, the model will give high probability to strings that are similar. So the operations such as matches and frequent insertions and deletions should hopefully have high probability, since they're not very meaningful in terms of changing the strings, while the probabilities of the starting a gap and extending a gap, they should hopefully reflect how common and how large the gaps are in any given domain.
I don't know if you're going to talk about this, but do you always have it be character by character, or
no? So you can. I mean, so
automatically learn, whether it should use blocks of characters, common chunks.
That's in the future work, actually. So I think that's actually one interesting thing is that the question is, how can you learn? I call them macro operators. How can you learn sequences of operations that are actually semantically meaningful? And after you learn such a sequence, you can just put it in the original model instead of the basic operations and consider it. I tried something very heuristic and it didn't work, but I think it can be done because it makes sense, which is the reason you asked the question. But you can certainly work. I mean, you can work with characters. You can work with tokens. As long as you have a sequence, you just define the probability of emitting observations, whatever the sequence consists of.
Right.
That works.
And in your experiments, did you? I don't know again if you're going to talk about this, but did you learn the emission probabilities for every individual character and every replacement character and so on?
Yeah. So one thing. So there's several levels you can do that. So for example, you can split characters into large classes such as punctuation, letters, and numbers, and so on. And one thing I found out is that if you have little data, especially, what happens is you don't learn very robust probabilities for just substituting Q for an X, because you don't observe a lot of Q to X substitutions. So in those cases, what makes sense is that you learn probabilities for those, but you also use multi-level smoothing, which is similar to actually things like deleted interpolation, shrinkage, and so on. So there's sort of a number of explanations for sort of doing it in a principled way. But effectively, you want to do some sort of regularization that takes care of this problem. So it helps quite a bit, actually. If you have a ton of data, of course, you can learn as a very individual operations as well. So on to experiments. So what we want to do is we want to see how well using this metric compute string similarity. And the way we will do this is we will do twofold cross-validation with equivalence classes of records. And by this, I just mean that we are taking a database. We have certain groups of duplicates in it. And then every group of duplicates gets assigned to one of the two folds randomly. Then we take the two folds, train in one, test in the other, average the results over 20 runs. And the way we test is we compute similarity for all the pairs in the test fold. If it's too large, we do some blocking. And then we start with the highest scoring similarity, with high similarity pairs, and then start labeling them as duplicates. And then going down, we compute precision and recall. That is, we compute, as we're decreasing the similarity, how many actual duplicates or co-referent pairs we've already identified, and how many of them are correct, and how many of all the co-referent pairs have we found. And F measure is just the harmonic mean.
How is the records labeled? Is it humans or is it ISP?
So in the data sets that we used, there was the restaurants data, for example. It's human label originally, and it's actually correct. It's small in a data set that I've looked at it. Several people looked at it, and it's correct. There's another data set, Quora, with citations, and there's a number of errors. It's it's been, I think, originally labeled by some extraction system, and then by some linkage system, and then human reviewed, but there's still bugs there. In some cases, like I don't show the results here, but we had some experiments with the product data. The UPC codes are they're basically provided by the merchants. So it's a combination of all these things. So the couple of data sets I show here. So one is this restaurant data, where we have multiple restaurant listings from two guides, where there is a number of restaurants that have duplicates among them. This Sightseer data set, where we have citations for, that's another actually big domain here, is that we have citations for research papers. And then there's 4 large groups. These are non-segmented, so they're just citation strings. And then finally, in Quora, we have citations where they're segmented into fields such as author, title, venue, and so on. So here are the results. We're comparing learned affine distance with static affine distance. And not surprisingly, across the board, we're getting improvements on the percentage of duplicates that are viewed as being highly similar. One thing that you may notice here, so we have very low results and relatively low results for these two. So these are actually somewhat noisy experiments, because what we did is we took the restaurant names and addresses, just those fields, and then viewed them as duplicates if they are in the coreferent pairs. However, what happens is you may have more than two restaurants with the same name, which are in different records in different cities. So with respect to the labeling, those two names are actually non-duplicate, yet they're the same effectively, and they are viewed as duplicate by the system. So as a result, there's this sort of artificial decrease of the results here. But I mean, these results are more or less indicative. And there's also results here, for example, where what we did instead, we took the whole restaurant record, and then we ignored these fields and put it into a single string, and then we just computed the similarity function, learned the similarity function, then computed similarity for the whole string. And the curves here, so this is recall, this is precision. So we're starting here where we're labeling the most similar strings as duplicates, and then as we continue labeling, basically we get most of the duplicates at some point, well, all of them at some point, but then at the same time we're starting to label non-duplicates as duplicates, so precision decreases. So in the learnable distance does much better than static distance here. So back to the overall linkage problem. So
before you move on here, did you compare it to other similarity functions like cosine, similarity,
Mm-hmm. Mm-hmm.
Did they work better?
Yeah. So let's see. I have another slide. So I'll have another slide later which shows cosine. So one thing. So for example, for a data set like this, I'll actually have a slide later which shows that cosine beats this, because what happens if you have a longer string, doing the similarity with respect to individual characters really is not the right way to do it, because you have multiple tokens, and really doing token-based similarity is better. If you have smaller fields, it actually helps to do it. I guess the bottom line is, one thing you want to take out from this talk maybe is that you should throw all the similarity functions into a bag and then learn their combinations. That's generally, I mean, so that ultimately if you want to solve this problem, to get a curve like this, you want to use all the functions they can and then train to figure out which ones do best. So generally what you want to do is you want them to be as diverse as possible. So for example, string edit distance really cares about the characters. Cosine cares about tokens being similar but doesn't care about order. Token-based edit distance would care about order, but would sort of, again, would be subject to things like swaps and long distance transformations. So the point is each of them captures sort of a different notion of similarity, and by putting them all together, you're really, that's the only way to ensure that you capture all these different notions of similarity and leverage them. But it's really, I mean, in different domains, you'll have different notions. I mean, so this is just for the short string. The point, I guess the bottom line is that for any domain, you want to learn as opposed to not learn, because you're adapting.
You don't make a model for each field in the record?
Yes. So this is actually, this is coming up. Thanks for the transition. So if we have multiple fields and we have similarities for the different fields, we also want to have a way to combine them, right? So that's not very hard to figure out. So the way that this can be done is if we have a vector of these different similarities for these different fields. So here, suppose you have this, back to this product offer data set. So you have these different fields, and for each field, you come up with a couple of functions. So say here you have learnable edit distance, cosine. Here you may also have something like extraction of product models, because you may have things like product models, which may be useful. For numeric data, you may just have numerical difference and so on. Basically, you have this bag of similarity functions, some of which may be learned, some unlearned. Hopefully, they're learned. So you're taking all of these for any given pair, computing the similarity for the fields, and then putting them all into a single vector. And then the question is, well, for this vector, we just need to figure out if it's similar or dissimilar. That is, it refers to the pair of records then as co-referent or non-co-referent. So this little box F star can just be any binary classifier that produces confidence estimates, basically corresponding to the likelihood of the pair belonging to the class of co-referent records. And a number of classifiers have been tried. Naive Bayes have been used for a very long time by statisticians, not surprisingly. And then in the recent years, several other classifiers have been tried, decision trees and SVMs first. But what we found is that if you have domains where you have a ton of data, such as the product offer data, for example, the problem is there's two problems really. One is that you have a ton of records you want to do linkage on, but at the same time you have a huge number of training pairs, because there's a lot of records that are coming in with the UPCs, and you want to leverage this, and they're continuously coming in. So doing something like SVMs would be, at least in the vanilla form, would be difficult. Although again, there's a number of new algorithms for doing it online. But what we did instead is there's this average perceptron algorithm due to Collins, which is a variant of the voted perceptron due to Freund and Shapir. And the nice things about it is that, well, one really nice thing is that it works really well in practice, as it turns out. And then several other things is that it's an online algorithm. That is, as new training data is coming in, the similarity function is being adjusted as we go without the need to retrain. Another nice thing about it is that it's a linear classifier. That is, if we have a system where people want to look at the weights on the different functions and say, no, this is really wrong, it gives us the weights. So it's really interpretable, which is a useful thing. They can, in principle, actually be negative, because what happens is, let me show the example. So suppose you had an attribute here, which actually would be more indicative of the things being non-coreferent. So for example, if you had, say, this is, I guess, a hypothetical example, is if you had a function which computed a distance instead of similarity, and say if you didn't want to, or you had some reason not to convert it to similarity function, you actually want to have a negative coefficient there. So back to the question that was asked about the learning multiple similarity functions for different fields. So what we did is, we want to now have this record similarity function where we're combining the individual similarities, but also want to see if using these learnable similarities at the bottom level actually helps. And turns out it does. So here what we're comparing is this results, the F measure on the linkage with the learned combined similarity function. However, here we're using either non-learned similarity here or learned similarity here. And we're still getting improvement because basically we have better, more accurate individual features on the individual fields. So it's still useful to do learnable similarity for the individual fields. And here is the PR curve for this. Again, just showing that by learning the similarities from the individual fields, you're getting an improvement. OK, so now this is all nice. However, the problem is that combining the fields is sometimes not possible, because in domains like this, we may have data that's just one long string, and we don't know what the fields are. So the duplicates here, again, if we just compare the strings, the duplicates are a little hard to get, because in some cases you'll get like cosine similarity quite high because of these chunks are common, yet these are different papers. One is a journal, one is a conference paper. So it would be nice if we could just take data like this and segment it. And this is done by information extraction systems, which are well known, and there's plenty of them. And what we would typically do is we would take some training data that is segmented strings, and then train an IE system to take citations and then split them up. The problem is, in this case, even humans typically don't know what is correct. So the issue is that if we commit to one of these now, effectively, if we made an error, we will not recover from it later. At the linkage phase, we will have now erroneous data where things have hopped from field to field due to erroneous segmentation. And the point is that errors made by IE would be unrecoverable. And as a result, it's possible that they would lead to cascading errors. So the way to solve this would be to do the two tasks together. That is, to do joint inference where the uncertainty of the IE system, which hopefully there would be some uncertainty associated with assigning this to this field or this field, would be propagated to the linkage stage. That would somehow be able to know that these two strings could be segmented either way. And there's been a couple of methods for doing this. However, typically they require training data sets for the individual tasks, and then the individual tasks are trained separately, and then they're combined in a single final training stage. So what we did was a little simpler, but at the same time, it possibly less powerful. It worked well for some domains. So let's look at this example. So if we have this addresses, really what we have is we have three segments in this data. We have the house number, we have the street name, we have the suffix here. So in the basic model, edit distance model, we would just learn separate parameters for the insertions, deletions, and substitutions matches, yet they would be the same for the entire string. What we can do instead is if we can know the number of segments or have a good guess about it and try different models, we can have a stacked model like this where we have transitions between all the states. So I'm just showing here transitions from M to the others, but effectively you have this cobweb of transitions going across all possible states. And hopefully what you would learn is you would learn the different parameters for different segments corresponding to each of the edit distances. Yet because you have this joint model, if you're not quite sure whether some chunk belongs to this part or this part, by looking at all possible alignments for this model, you're able to take this uncertainty account when computing similarity. And another nice thing about this compared to the other approaches to this is that with this model, you're able to use all sorts of data within the same training framework. So if you have, for example, a lot of examples of things that are both segmented and are known to be coreferent, you can use this by training this with EM.
Is there an operation when you're extracting the segment? So just extracting one segmentation, is it possible to get multiple?
Yeah, you can.
So in such a case, can I not take the multiple segmentations and try
Yeah, you can.
one
Yeah,
after the
you
other?
can.
And wouldn't that be a simpler approach than learning this?
It would be. Yeah, yeah, it would be. That's a good question. I don't have an experiment. Like I haven't ran that baseline, but that would be a good baseline. Yeah, thank you. I should do that.
Can you go back a slide?
Yeah.
So once it transitions from the number to the street, sorry, to the street number, and then would there also be transitions from like the M down?
Yeah. So there's, I mean, all the state in the limit, all the states are connected. So you have transitions from any state to any other state.
So you allow them to go back up also.
Mm-hmm. Well, I mean, so in some domains you can have constraints. So for example, if you know for addresses, I mean, one thing is the question is how much engineering you put into this thing.
Yeah.
So if you know that for addresses, for example, you never go back to a number from the street name,
Right.
you would just disallow transitions there, or you would.
Right.
I mean, another thing is that if you're learning this from data, and if you'd never observed this transition, they would have an extreme. I mean, the only probability they would have is due to smoothing. So it's hopefully would naturally sort of learn that even with all transitions, some are extremely unlikely and they would be
So
downscored.
that's my question. I was going to ask on the next slide, like, how do you handle swapping order of things? But you're actually allowed to go back and
Yeah.
go through the
Yeah.
fields, not just
Yeah.
linear.
Yeah, so with this model, we can train it using different kinds of supervision. We can train it using these segmented pairs of strings where basically we would where EM would maximize the alignment of these while knowing that certain emissions occur in certain states. If we have just unsegmented string pairs, again, we're just using maximum likelihood and considering all possible alignments across all the possible segmentations. If we have just individual segmented strings, we can just train the transition probabilities between the different segments of the model. And then finally, there was a nice paper last summer in ICL which showed that even with completely unlabeled data, you can actually get comparatively good results for segmentation with a few things like just with a few human engineering tricks thrown into HMM training. And again, the tricks that they have proposed can be used in this model as well. So the reason why this is useful for this domain, so here this is back to the restaurants data set. And here we can see, so here's the curve for TF-IDF that was asked before about. So here, for longer strings, of course, using unordered measures such as cosine does much better. However, we're able to sort of beat it still with edit distance along with this segmentation if we're putting in this complex model. So the baselines we ran is let's see, I think I have a slide later. No, I don't. So if you have a lot of data for segmentation, and the domain is fairly unambiguous, actually you probably would do better by just having a segmenter. If you don't have a lot of segmentation data, the nice thing about this is that it's able to learn the segmentation with fairly little segmentation data, but just a lot of duplicate data. So we're sort of this notion of using indirect data for training. That is, we're using data for a different task to learn to do well on another task. And it's really sort of where this joint inference model shines, is where you cannot learn one task on its own, yet by putting two tasks together, you're able to use data for one of the tasks to learn the other.
And the order of the fields in which the citation, most of the examples you mentioned that authors, titles, and journals of
So there's
the order for repeating among the examples, would that be learned as well, or would that?
the order of the fields.
Yeah.
So I think the order. I mean, implicitly, if you have once you learn the transition structure between the segments, you can think of like what would be the most likely transitions and so on. So it's implicitly learned, but it's not learned explicitly in the sense that it's just learned in the Markovian way. Basically, you know what the next most common thing is. You can integrate it and sort of look at like things like just what would be like the random walk that's most likely and so on. But yeah.
So when you do joint inference, do you do clustering anymore? You don't do any clustering, right? I mean, you don't do any classification. Do you do classification?
Classification for.
Previously you have different.
Yeah.
Yeah.
Yeah. So for this, so here we're considering records which are just a single field. So if we have multiple fields, we would want to do classification. Well, effectively classification because we're combining the similarity between the multiple fields. So here, we're just comparing a single similarity function, which is TF-IDF or different kinds of edit distance. But if you're having multiple measures, you certainly would want to use something like. I mean, it's more like regression actually than classification because you're predicting a numerical measure. But yeah, but you would combine them in that framework.
This is a very basic question. So how does this compare with just applying parameter different? If I'm comparing phone numbers, for example, I know that if any number is different, they're different. But if I have parentheses, that's fine. And so I'd like to build addresses are the same. I know I should have
Mm-hmm.
why not just directly build in that information?
You can. I mean, so if you have a very trivial domain like phone numbers, sure, you can have a. I mean, you would not take long to just hand code a correct function, which is ignore punctuation, just do, and like maybe have one at a distance at most, like one typo. But the thing is, like in some in other domains, it would be less trivial to come up.
The citations is a good example. But the things like addresses, I mean, how does this compare with the sort of hand-craft grammar?
So for the addresses that we observed, the thing is in the restaurant data, for example, so there's two kinds of addresses. So one later I'll show one experiment. There's another data set called dbgen, which is this automatically generated addresses. It was done by people in Columbia. And there you have things like PO boxes. So it's less trivial than it seems at first. But the restaurant data really shows that it's actually a lot less trivial than it even seems after the second thought. Because what happens is if you have things like between 45th Street and 61st Street, in parens, next to Central Park. So I mean, there's actually in real data you end up with a lot of these things which are not regular. I mean, so in the ideal case, all data should come from some gazetteer which looked at the zip code and found the canonical address. But at least in the address case, like it's actually not true that the data is very regular. So
that example will not be handled by yearly distance either, right? Between 45th and 46th Street. I mean, if there is an example that can be handled this way and cannot be handled with some rules, and I don't know, I would do cosine on word bigrams, not on unigrams. But and then you keep the order. So
yeah. Well, I mean, so one thing actually, so even for shorter strings, I argue that edit distance on tokens most of the time will be, if strings are short, edit distance, unless you have a ton of swaps, edit distance will be more accurate than cosine because order still matters a lot of the time. So I guess the bottom line is that you can generally sort of the question is you can always hand code some intuition into these things. The question is there's always room for learning. I mean, I think the ideal way to do these things would be combining hand intuition and learning. I mean, that's so.
This is sort of one extreme, right? This is more learning. The parameter is more
Yeah, yeah. So I mean, in the ideal case, I think what we really want is we want learning method that can easily incorporate human constraints and human supervision. I mean, that's the right thing to do these things really. So the argument again for interpretability of functions is that you want things that are easily interpretable, and if you see that something is wrong or something is not doing right, you can tweak it and hand constrain it and so on.
In principle, you can go it as an error similarity at the field level. Suppose the strings are identical according to the specific grammar that you are encoding. When it's 0 or 1, that's a Boolean similarity.
Almost like a filtering, right? So you can filter based on your grammar, and anything that you can't filter based on grammar, you can pass it along and let it go.
All right, to sum up, so learnable training distance really helps with capturing the specific notion of similarity for each field's domain from training data. What that means is that if we have different importances associated with different edit operations and so on. By learning these, we're able to figure out what's important and what's not. At the record level, it really helps to learn because it helps us to identify what fields are important, what similarity functions are important, while all the others are irrelevant, noisy, or less important for classification. And then finally, we're able to improve similarity computations by using joint inference because in some cases where we data starve for segmentation data, we can learn segmentation by using this duplicate data. So on to a different topic, clustering, which is this nice task of trying to find a partitioning of a data set into groups or clusters such that objects in one cluster are similar, objects in different clusters are dissimilar. And the thing about it is that just the similarity is ingrained in the task. That is, all clustering algorithms, they depend on some similarity functions either implicitly or explicitly. In some cases, we want to compute the similarity matrix or be given a similarity matrix where the similarity computations are performed. In other cases, we want to just have some probability model which then corresponds to some similarity function between the different instances we have. So the example of clustering, suppose here we have some two-dimensional data, if this is some marketing data maybe. And if we just give data like this, we can have clusters like this, or we can have clusters like this. And the problem with clustering is that we don't know which is right, which is a problem with evaluating a lot of clustering algorithms. So semi-supervised clustering is a variant where you're given both supervised and unsupervised data. And then we want to still get the partitioning into the meaningful groups. However, we have these two possible forms of having supervision. That is, we may have some instances which are labeled with the correct cluster they should belong to. That is, we have some subset or all of the clusters labeled, in which case it just becomes classification in the limit. Or we may have pairwise constraints. That is, we may have certain pairs of instances which are labeled as belonging to the same cluster or different clusters. We call them must link and cannot link for more or less historical reasons. And in the general case, we want constraints are more general than labels because they can always infer constraints from the labels, but not vice versa. So what this data really gives us, well, among other things, it gives us a way to initialize clusters, but it also allows us to adapt the similarity function using the supervised data. Because this way we can effectively see if these things should be in the same cluster, it's quite likely that they would be similar, and vice versa. And the way this can help is, again, going back to the toy example is shown here. Suppose we have this data, but now we have a couple of examples of things that should be in the same cluster here, or things that should be in different clusters. And if we just modify the similarity function, which corresponds to effectively stretching the space in the horizontal dimension and then compressing it in this dimension, now the data looks like this in the transform space. And here, the clusters are much easier to identify like this, and the resulting clusters respect the constraints that the users have given. So this has been considered by a whole number of people, and the two approaches they typically have pursued. One is constraint-based, where we just change the clustering algorithm to avoid violations. That is, we just take an algorithm and put in somewhere a check, and if constraint violated, then go back to step one, or try something different, or return error. The metric approaches, on the other hand, they typically take this supervision data, they'll learn some similarity function, and then plug it into the existing EM, k-means, graph partitioning, hack, and so on. And what we really wanted to do is we wanted to have both of these are clearly good things. So what we want to do is integrate the two approaches so that we can do the similarity function learning and avoid the constraints in the algorithm simultaneously. Because it allows us to learn, well, first of all, it allows us to learn as we go. As we're clustering, we can always continue modifying the function if it see that it's better, it works better this way. And it also allows us to see if an algorithm, to prevent the algorithm from violating constraints as the constraint methods. And the framework that we used for doing this integrated model is Hidden Markov Random Fields, which have been used by vision and image processing researchers for a number of years. And at the same time, we didn't do, but I mean, it's possible to consider a number of other probabilistic factorizations based on other TLAs that a lot of you know about. So what does this look like? So here's a picture that I hopefully will explain because it doesn't look very clear. So we have some data. We have these x's. And you can think of these as basically vectors in some space. And for each x, we have a corresponding random variable, the L, which encodes which cluster the x should be in. So this current clustering, the encoding here, so these are in one cluster, so this corresponds to one cluster here, and then one cluster here. So this can be formalized as having a Markov random field at the top level. So we have a Markov random field on the labels, on the variables, on the random variables corresponding to the labels. And then we also have this observed data here. And then the entire thing, therefore, is called an HMRF because the labels on the assignments are hidden. We don't observe them, but we do observe the actual data we're given. So now if we, given some set of constraints such as these, if we have some way of modeling the probability of observing a certain configuration, a certain cluster configuration, given these constraints, so it's the probability of observing all these labels given the constraints. And then we also have the data likelihood that is given the current assignments of the labels. We just have a generative model for observing the data, just like a normal EM and k-means. What we can do is then we can have this joint probability function, which models the joint probability of observing the given data to us, and then the labels assigned to them, which then can be factorized as the probability of observing the labels and the probability of observing the data. So then the overall clustering goal can be formalized as trying to find such labels on the data that this probability is maximized. So it's just the joint likelihood maximization. And this can lead to an objective function like this. I'm skipping a bunch of steps because I want to talk about more things at the end. But so take my word for this. So here what we have is having this model leads to this hairy-looking thing. But what it really is we have a term here which encodes the density of each cluster. That is, we just have this distortion or distance function parameterized by some parameters a, which measures the similarity between each instance and the mean or prototype of that cluster. So this is just like a normal k-means or in EM. And then we have these terms here, which penalize certain assignments that violate the constraints. So here what they do is for every constraint, so these are must-link constraints, cannot-link constraints, if the 2 points in that constraint are assigned to different clusters, and they should be in the same because they're must-linked, we have a penalty associated with that violation. And the penalty is proportional to the current similarity function being used. So this implicitly, this intuitively corresponds to the fact that if the similarity function tells us that these 2 points are really close together, and we really should know that they shouldn't be, what this indicates is that the similarity function should be changed, basically stretching this dimension to make them further apart, so that the constraint can be satisfied easier. And likewise for cannot-link constraints, if we have pairs of points which should be in different clusters, they're in the same cluster. What this shows that actually, sorry, the previous example was for cannot-link. So if they're in different clusters and should be in the same cluster, they should really shrink the space. If they're in the same cluster and should be indifferent, we should extend the space. And this is done by having this penalty take into account the current distance metric. And in this model, in the Markov random field, that corresponds to the potentials associated with the violated, with the pairs of the constraints that are violated. And then we have a normalization term here. So we have these two. We have the cluster distortion based on the distance. And then overall, the nice thing about this framework is that this can be a number of different similarity functions. So the 2 classes we considered, one is Bregman divergences, which include things like weighted Euclidean, weighted Mahalanobis, weighted I divergence, which is a Kale divergence extended with where we don't require them to be probabilities. Or this can be weighted cosine similarity. So the algorithm can be used with different similarity functions for different domains.
Can you explain how is this different than adding weight to each feature when you are clustering?
So effectively, so I guess one thing I could have shown and I didn't is if you write this out as dA, for example, for Euclidean. So dA in this case would be the sum of all the features minus prototype squared with the weight. So effectively, A is the set of weights on all the features.
Oh, and then beyond the weights, the other factors are just adjusting the weights to what it should be than what we initially thought.
Yeah. So the thing is, the way we maximize this function is in EM-like procedure where we have a 2-step. So in the first step, we assign every point to the prototype that's nearest to it. And then in the second step, we move the centers of the clusters and we modify the distance metric. So we're iteratively refining both the clusters by moving the centers and the distance metrics. So we're effectively transforming the space, just like we do in k-means or in AM, for example. So that's a good question. So one thing that makes, so there's, again, we can come up with different factorizations here. So if we have an A that's just diagonal, we have Euclidean. If we have an A that's non-diagonal, but say constrained to be positive semi-definite, we have weighted Mahalanobis. So it's a question of sort of how complex we want the similarity function to be, and then how much we are sure that we can learn something decent with this model that could be used. Yeah, sure, of course. If you have Mahalanobis, you have the x minus a, then So you're transforming. So effectively, what you're doing, you can. So it's a question. So the weights, they correspond to transforming the space for each cluster. So here we're sort of taking the clustering, and then each cluster has its own shape, and then for a non-diagonal case, we're effectively not just stretching it, but we're actually doing the complete transformation, the projection of into a different subspace. And so this algorithm, this objective function leads to an iterative algorithm where we optimize the objective, and as a result, we get the clustering at the end. So why this works? Here's an example of why this works. So we're comparing just basic k-means, which does not so well. And then we're comparing on some text data. So this is with a weighted cosine. And what we're comparing with is comparing with using this framework, but without learning the similarity functions here. So the way we're using the constraints is to initialize the initial cluster centroids. Shugaru Basu, who I did this work with, so he had several nice papers on coming up with good methods for initializing clusters. And then here is the curve which also integrates the learnable similarity, and it shows that basically learning different weights for the different clusters, different sets of weights, different parameters for different clusters helps. So to summarize the clustering and learnable similarity functions for clustering, learning similarity functions really helps because it uses both labeled and unlabeled data. In this algorithm, we're estimating the similarity function using both the distortion of each cluster, like in EM, and at the same time trying to modify it so that the constraints are respected. So again, it sort of goes back to this data-driven variance. So we're not just taking the variance in the data into account, but we're also combining the property of the data with supervision. At the same time, the model allows us to leverage on this nice algorithms for seeding and soft constraint penalties to bias the algorithm to respect the constraints, along with the similarity functions. And the probabilistic framework really helps as opposed to early algorithms that are constraint-based because supervision can be noisy. And there's a number of early algorithms which just, if there's noise in the constraints, they may just not converge. So here, we don't have this problem because we just have the probability-based formulation.
Based on what you described so far, your approaches are very specialized, right? They are very aggressive learners, kind of, right? So have you considered the problem of generalizing?
So one thing here, if you notice, so one thing I didn't talk about is there's this term ZA. So ZA here, this is, so it comes, there's actually several terms within it that come from the original probability formulation. But what it can include in prior on the weights. So for example, if you say that I really know that the weights should not change much from what they are because that would be just junk, what you can do is you can formulate as having a prior on this matrix. And then by having this prior, this would go into this term, you would effectively penalize A changing too much from this direction. So in a way, you have leverage there. If you know that certain things should not be learned, you can prohibit them from being learned by having a prior. Is that the right question that I gave the answer to?
So my domain, like the domain which I deal with is malware, right? Also viruses and spyware. So what happens is we always, if we overfit the data, the new variants always get missed or misclustered or misclassified. Never approach it.
Oh, I don't think. So this is a model-based approach. So we're trying to find these nice clusters with these prototypes and so on. There's a number of tasks where basically model-based clustering should not be used because it's just not the right way to do it. I mean, something like graph partitioning, basically, because if you don't have data clusters which are sort of this prototype-based or probability density-based and so on, this can fail very miserably. So we've been. Especially if you have data where you don't have this nice numeric space where data lies. quite possible that it'll fail miserably. So.
So I got a question. So you talked about combining these constraint-based methods with the metric-based methods. But I'm not sure, but this could be a stupid question. But this looks very much like a UL formulation of the constraint-based methods. I'm not just have that.
Yeah. Yeah, I don't see it immediately. I mean, we may take it offline, but it sounds plausible. But we didn't consider it at all. I'm trying to think. So I think, so at least, so I guess, well, one thing is like the constraint-based methods are different. I mean, some of them would just basically say that if you have this k-means time procedure, so one of the early algorithms would just say that when you're assigning the points to the centroids, you are try to avoid all violations. If you made some violations, you restart, and if you after a bunch of restarts you failed, you just fail. You say there's noise and so on. So in terms of the dual formulation, I don't know.
So because for them they're trying to maximize this cluster distribution, but they have this hard kind of constraints they also want to satisfy. So it's kind of very much like constraint.
Yeah, well, I mean, so yeah. So I mean, we are. So the thing is, by having these two terms, we are trying to satisfy the constraints.
Yes, but
Yeah.
but if you put your constraints into your objective, it's very much in the space, right? I'm not quite sure.
Yeah, I mean, it could be also like my lack of optimization knowledge that's failing me. So, yeah. But this.
All these constraints are inside the vector function. They're not really constraints. They're not in the equal sense. They're just soft objective function. They can be violated. There's no hard constraints. Right?
No, we can always. I mean, that's how these terms come. They come from violations. Okay. So overall, I guess the bottom line was combined approach does better than the individual approaches and better than supervised clustering, not surprisingly. Yay. All right. So now this final piece here, which is very recent work, and this has not yet been reviewed, so any comments and criticism is very, very welcome. So one problem, so this is going back to blocking, which people asking questions about. So the problem is that many record linkage systems and clustering algorithms require similarity computations. Okay, we're all convinced. But the problem is that there is this O of n squared computations if we do it for all the pairs. So really, in a lot of cases, most of them are unnecessary. If we have a McDonald's in Georgia, we don't want to compare it to restaurants in LA in our restaurant data set. It doesn't make sense. So what we want to do is to have a blocking methods which select some subset of candidate pairs using indexing or sorting or some sort of fast way of limiting this pair space. So an example for citations, for example, we may have a heuristic such as we only care about records where the year is the same or within one, maybe, and if there's at least one common token in author. And this is just one example. And this is really related to the fast nearest neighbor search, which has been considered by database and algorithms researchers for a number of years now. And it's very well studied. But the problem is that typically, at least as far as I know, most of the methods that have been developed, they rely on either the data lying in some low-dimensional metric space or in high-dimensional space where it gets projected into low-dimensional space, or it assumes that there is some underlying, if it's string data, that the string edit distance is the correct similarity function, and then we're finding some projection into the metric space that satisfies the string edit distance and so on. The problem is that if we have domain where there's multiple heterogeneous fields, such as categories, prices, and so on, mapping it to a low D or high D metric space is non-trivial and can really hurt. And in those domains, really using predicates, such as the ones shown before or the ones here, may be much more appropriate and may, again, allow us to incorporate human intuition much better than using the mapping-based methods. So here, I mean, we can have predicates such as the exact match on some field, or if we have a categorical, like the things lie in the same subtree, or the abbreviation match. Basically, there's a number of different predicates when defined for string, numerical, and categorical, and so on data. And typically, what has been done in the past is people have assumed that some number of these predicates that's optimal for a given domain is given, and then we learn a good way to block. So given some blocking function, we learn how to block, and then we do the blocking efficient. Well, what we wanted to do is we wanted to make the blocking function adaptive. We wanted to learn blocking. So what would be an ideal blocking function for any given domain? It should hopefully return all or nearly all positive pairs, that is, the coreferent pairs or same cluster pairs. And at the same time, it should return the minimum number of different cluster pairs just to be efficient, since that's the whole point. So then if we go with this predicate-based approach, what we want to do is then if we have a training data set, so we have a bunch of labeled duplicates or pairwise constraints, we want to learn this function as a combination of these basis predicates, where we can have these predicates for different data types, numeric string and so on. And then we want to, based on these applied to all fields of appropriate type, we want to compose some blocking function, which will then give us all positives and a minimum number of negatives. And the two formulations we considered, one is if given this large pool of basic blockers applied to different fields, we can have a disjunction that is, we'll say something like if authors have a common token or same year or so on. Or we can have a DNF, which would be much more expressive clearly and would allow us to have a disjunction of these multiple predicates. So to formalize it a little bit, if you like this formalization, so what we want to do is we want to find a blocking function f sub b, where b is this set of all predicates, such that it returns all or nearly all positives. So it returns 1, we assume that it returns 0, 1, and it returns 1, it means that the pair is blocked. So for all positives, we want to return 1, possibly making epsilon errors, because in some domains it's actually impossible to do to have all pairs if you block. And then at the same time, I want to get a minimum number of negative pairs, which the blocking function returns. And then in the disjunctive case, this blocking function, if we associate a binary weight with every predicate, and then the ones that we select for the disjunction have 1, the ones that we just don't care about have 0, and B for this pair of records is this vector of 1s and 0s, so each predicate returns a 1 or a 0 for a record pair. So this f sub b is basically a 1 if the disjunction returns true, or a false, or 0 if the disjunction returns false for this pair. So basically we have this formulation where we have effectively an integer programming problem for this binary weight of vectors corresponding to selecting some predicates from this large pool. In the DNF case, this b will be and w will be larger because here we'll have to consider a number of conjunctions. In the limit, we'll have the exponential number of all possible conjunctions. Yeah.
You said on a couple slides back that people use these blocking predicates already before.
Yeah.
So is the difference that your blocking predicates are generic predicates for all domains?
Yeah.
And when they did this before, did they also try to automatically learn these disjunctions and stuff?
No. As far as I know, no. So the closest work in actually last year, William Winkler, who is this very prolific statistician who's done a ton of work on record linkage, he had a nice tech report where he considered the problem of judging the accuracy of a given predicate. So given the predicate, he basically had a strategy for estimating how well the predicate does. But as far as I know, I don't know of anyone who's done this learning the predicate combination. So. Oh, yeah, it is. And the way we went about solving it, well, approximately, of course, it's so tough, is it turns out that this problem actually maps to this red-blue set cover problem described by Carr et al. In the Soda 2000 paper. So if you recall the classic set cover problem, what you have is you have a number of sets. So if the classic set cover, you would ignore this top layer altogether. And you have these sets, each of which contains a number of items in it. We've shown, and the edge connects a set node to an item node if the item belongs to a set. And you're trying to find a subset of the sets so that all items are included. That's the classic normal set cover. So in red-blue set cover, you have two types of items. You have the blue items, which are good, which you want to cover. But at the same time, every set has a cost associated with the number of these negative items you're trying to cover. So this, as you can see, exactly maps to the blocking problem. Because what happens is these corresponds to the positive pairs, which we want to retrieve all of them. That is, we want to cover all the positives. And at the same time, we want to get a minimum number of negatives. So in other words, if we think of the sets as blocking predicates, where each predicate covers positives and negatives, we want to find a subset of the predicates such that all positives are covered and a minimum number of negatives are covered. So in the same year, Peleg proposed, so there's a couple of, so there's been two approximate algorithms that I know for this. So the problem is NP hard, not surprisingly. there's both there's upper and lower bounds both. So it's actually it's really hard. But there's two approximate algorithms which are quite good. One is de-duplication. The other one I can't recall who did it. But the thing is that it's based on so it's an integer programming problem, but it's based on LP relaxation. And there, if you recall, in the blocking case, the number of these pairs is huge, right? And there'll be some blocking predicates which are just really poor in the sense that they'll grab a ton of data. And it's going to be, I mean, just when you're going to the actual code and optimizing it, it's actually non-trivial to do this efficiently. So what we really want is we want something that gets rid of the bad predicates really fast. And really, Peleg's algorithm is greedy. And the nice thing about it is that early on, it throws out a number of the sets of predicates in our case, which are clearly poor and that get too many negatives, even if they get all the positives. So we basically adopted their algorithm for the blocking case, and there's a couple other issues. I guess time-wise, I'm pretty torn. But so there's also issues in terms of if you have a lot of data, how do you? I mean, you can't form this graph obviously since it'll be a squared number of items. So how do you subsample and so on? And for DNF formulation, what you would have instead of just these nodes here, you would also have more corresponding to the conjunctions. So you will take basically all combinations of these guys, and then the edges coming from them would be the intersection between the edges of their between the constituents. So for DNF blocking, there's also a first step because we don't want to consider all conjunctions. So there's a two-step greedy algorithm where first we select the conjunctions which are most promising, and then we create the overall blocking functions from predicates or conjunctions. So that's what we did, and here are some results. So the results here, so what we're showing is given all the bad pairs, all the non-coreferent pairs, the question is how much blocking saves us by filtering those out. And here this just tells us what percentage of the negatives we retrieved. In the core case, actually, this seems high, but if you recall, it's a very dupe-dense, so to say, data set. That is, there are very few original objects, and there is a ton of duplicates. So there's very many positive pairs which you need to cover. So the red set in the previous slide is very large. So it's hard to cover it, in other words. So you're paying a higher cost in terms of negatives. Another problem is that you have a lot of these cases like the journal paper versus conference paper, which again are sort of non-trivial examples. And again, coming up with a good blocking strategy sort of has a cost of getting more negatives. So this is the restaurant data. This is this DBGen, the people addresses and so on, and zip codes data that's automatically generated using a mutation program from Columbia. So what we learned is that, okay, so disjunctive does worse than DNF, not surprisingly. DNF, having 3-term DNFs helps over 2. Going further does not really help. At the same time, what we learned also here is that for I forgot what we learned, sorry. The bottom line is, blocking, I know what we learned. What we learned is, that after thinking about it, the way this relates to the whole problem is this predicates can be viewed as similarity functions. Basically, this disjunction, any disjunction or any DNF, it's sort of a cheap, logic-based similarity function which says that these two things are similar if they satisfy some predicate or some set of predicates. So effectively, what we're doing here is we're learning more. These guys are obviously more expressive because they can have more features in there. They can say, match on this field, sort of match on this field, and so on. So having this expressivity helps to a certain degree here, but after a certain point, that's why it's not a sort of a very good similarity function in the pure case, because it's not very accurate, but it gets the job done for blocking because it needs to be fast. So what this leads to is the fact that blocking functions are computationally cheap similarity functions, which through sorting or indexing allow us to compute similarity between data really fast for subsequent similarity computation using the methods we talked about in the first half of the talk. And then another nice thing about this part is that really here, most of the time, similarity functions you're learning for accuracy. And generally machine learning people, they learn for accuracy. Well, here we're learning for scale. And this basically this allows us to scale record linkage and clustering up to large data sets. But it's sort of a nice, different look at how learning is useful. It's not just useful for 0.5% improvement in accuracy. It actually allows us to go to big data. And the bottom line is that it allows us to adapt into new domains without the need for hand constructing appropriate predicates for every type of data. We can just take a data set. If we have examples, training examples, we'll learn what a good blocking function is.
Do you have an example of a domain where this worked better than the previous work? I don't like handcrafting stuff as much as that's like that. It seems like if I'm comparing papers, allowing plus or minus 1 year for this simple thing to do. So there's a lot of prior knowledge that would really zero in on really good blocking functions. So do you have an example of where just doing it purely automatically like this beats all the previous work, which was just sort of had a handcrafted?
So the problem there, so I constructed a couple of sort of hand baselines, but I think is like I didn't know. So for the dbgen data, again, it's not real data, but there would be another, I guess, thing here. But there's a couple. So in the Winkler paper, he came up with several predicates, which such as like match on the first letter of last name and same zip code type thing. So we tried the predicates individually, and they did worse. But then again, I don't recall. In the paper, I think there was no like, here is a good blocking function. It was more of an individual predicates. So we did better than individual predicates. But again, like I guess the same for papers. I think I tried some like the same year within one, and common token and author, and then common token and title. And again, it did worse. There was no incentive for me to spend more time on it, so I didn't. But it's a good question. I think the question is.
Well, the converse of the question is, if you look at these predicates that you get, the blocking ones that you learn, and you'd think that'd be very informative about the kind of data you're dealing with. It might say, yeah, year minus 1, but not year plus 1.
So I didn't. I mean, for year, I considered only plus minus 1. I didn't consider it wasn't directional, but yeah. So I looked at the learned predicates. I mean, they all made sense. So for restaurants, like the first ones to be selected are usually exact match, because generally especially on the informative attributes, if you have an exact match, that's likely to get a ton of a bunch of positives and almost no noise. So one thing is sort of the bias of this whole algorithm is going to be towards this, high obvious exact match predicates on the high informative attributes. I didn't really see anything that would be sort of insightful about the year plus 1 and minus 1 and so on. But I think it's a question of constructing. I mean, again, so how, if you have more expressive predicates, you could probably learn more from those. Yeah.
So you actually went in an opposite direction from what I thought. If the predicates. So in your case, the predicates are, I guess, pessimistic. So you do disjunctive of them, but you could, or optimistic. I don't know, one way. But you could have predicates that are the other way, where if the predicate is chosen, it's almost guaranteed. Like some of the examples you gave, where if the address field has any number in common at all anywhere in it, and then you could have a conjunction of a number of these things. Did you try like conjunction at all?
So you mean in here instead of
instead of a disjunction. Well, I mean, I guess you have the DNF.
So conjunction, So in the limit, you could just learn one. I mean, I guess that would be a subset. Yeah, you could learn one.
Instead of having a disjunction of 10 predicates, you could have a conjunction of 10 things, and then your predicates, instead of being things that are very likely to mean that they're the same, they could be things that basically they have to satisfy this if they're the same, and then they're really weak things, like they contain a character in common.
So I mean, the thing is, like, there's really two objectives, right? Like what you're talking about, I think, is more like having good precision. So having a good conjunction will lead to better precision because the pairs would have to satisfy more constraints to be selected. Right. Well, the whole blocking idea of blocking is you're going for recall. Like you know that you will not. Your loss is very biased, right? You know your task is sort of if you think about it like a binary classification, you want to make sure that you label all the positives correctly, and you just suffer basically loss based on the count of the negatives that you misclassified.
Right. But it seems like it's just approaching the same problem from two ends. One side is you've got these easy constraints, and you would conjunct them, and the other side is you have these hard constraints and you disjunct them. And it just seems like you're coming at it from the top or the bottom, and you've come at it from one way, but I don't see any reason why coming at it from the other way wouldn't.
So you're saying like you would learn so in the first step of the DNF algorithm, we're learning the conjunctions. So is that what you mean by the other way?
Because that's what I'm saying. Except instead of, I mean, what you had with the DNF was you had conjunctions that were limited to 2, or conjunctions that were limited to 3, and then you didn't really gain much beyond that, right? And I think it's sort of a choice of what your predicates are. If your predicates, in this case, your predicates are, if the predicate is true, then it's likely that it's very likely that the thing is a match.
Mm-hmm.
But not all matches have to have that predicate be true.
Mm-hmm.
But you could go the other way, where instead of having predicates like exact match and same percent characters, you could have, are they, do they have any character in common at all, or
Well, like common token would be that, right? Effectively,
token,
yeah.
I guess it just seems like if you have predicates on that side, then a conjunction would make.
Yeah. So I mean, so these guys, so most conjunctions that I looked at, they wouldn't. So the stronger predicates like this would be by themselves often, and these guys typically are not selected by themselves because they're just too broad. They cover too many negatives. But within the conjunctions, once you sort of you basically make it a stronger filter, then they get selected.
Right.
Yeah. I mean, another thing is, some of it also could be a property. I mean, the question is whether just the step that gets selected is a property of the greedy algorithm, and like really by changing the greedy algorithm, we would get basically different disjunctions and so on. So.
Just real quick, sorry. We only have like 2 minutes
Okay.
left, so people can ask.
All right. Well, actually, all I have is like future. Let me show what I want to do.
Let's just do that and we can go.
Yeah, and then we can do the question. Yeah. So anyway, blocking can be learned. So what I learned from 6 years in grad school, and what I want to do. So one thing that's sort of the joint inference task. If you recall the whole segmentation and similarity at the same time, I mean, what I really liked about it is that the fact that you were using indirect supervision to learn for a task. That is, if we have little data for one task, but a related task that has a ton of data, how can we sort of do this? I mean, so transfer has been talked about, but it's not the same as sort of transfer in this case because I really think of it as learning from indirect supervision. And this can be many things. It can be like supervision that is weak, noisy, labeled. I mean, one sort of related work there is like there's a couple of nice papers by Thorsten Jakobs on improving ranking functions by just using the way people click on stuff and so on. So how can we sort of leverage this weak or noisy or indirect supervision in different tasks? Learning for scaling up also I sort of think it's sort of an interesting area where different things can be done where in this case we used advanced, one thing we want to do is that the indexing we used was quite easy, for example, for the common token. There's some nice work on having better inverted indices and building them selectively, so that could be integrated, hopefully getting better results. Another thing that it's very ambitious, and I know it can be done, but I thought of it and I talked to somebody about it and it seemed to make sense, is that in SVMs, the problem often is that you have to construct the matrix, the kernel matrix, that is the matrix of all evaluations of kernel for all the pairs. If you have too many pairs, you can't do it. At the same time, blocking cannot be used trivially because there are certain constraints in the matrix. It has to be positive semi-definite. How can we do blocking for SVMs? I don't know. I don't know if we can, but it seems interesting. If somebody knows, tell me. And then just general learning for scaling up beyond blocking. I sort of would be, if you have any problems that would be in that direction, I would be interested in talking to you about it. And then learnable string similarity, I mean, that's a lifetime worth of problems there because you can always come up with different domains where different strings have different notions of similarity. And then, things that I sort of think the next obvious steps is one thing. It would be nice to combine character level and token level similarity. There's been a couple of algorithms for sort of doing TF-IDF while allowing inexact matches. Again, if we do this adaptively, hopefully we would get a better function there. Also, having things like long range, so doing edit distances with long range operations, typically that results in horrible computational cost. So doing this efficiently, sort of an interesting question. And then finally, what somebody asked was about Matt asked about macro operators. How can we learn that in natural language, certain sequences, say ing, is a common suffix, should be ignored, and so on. So I've done some very simple, stupid heuristic thing. It didn't work, but I think it could be done right. And then, okay, conclusions just rehash all of this, so I'd rather take questions than do conclusions.
Really, really fast. We're trying to get a couple questions.
Yeah. I'll show this in case you want to read it. But.
Good question. For the blocking, do you do any efficiency experiments with this or timing? Or
I didn't do it, but I mean, effectively, what this is directly savings in efficiency, right? Because every negative pair that you didn't block, you have to compute the similarity for it. It means you compute edit distance for every field, and so on and so on. So effectively, this is direct. I mean, this directly translates into efficiency.
Well, you have to do some work in order to start a blocking function.
Yeah, well, but that's the training stage, right? So yeah, the point is that.
But in the first part of the talk, you mentioned some kind of heuristic similarity functions that will get you the same effect of blocking, right? They just transform.
Yeah.
So I was wondering how much. I think Chris was asking that.
Yeah. Yeah, so like I said, I compared to so in core I compared to the basic the same year, basically I compared to sample simple one. They did worse, but I didn't dig very deep. So I guess I could show it, but I feel ashamed about not coming up with a stronger baseline. But then again, I don't know of a classic baseline for the dbgen. There's a number. I tried the predicates of Winkler for the census data, and they all did worse. But again, it's not a fair baseline because they're just individual predicates. Yeah, I really if you are doing matching. If someone does this professionally, tell me what I should use because I don't know. So, yeah.
Okay, well, thanks.
Well, thank you.